previously, we've seen the chain rule written with Lagrange notation, written with a bunch of different primes. But there's another way to write it using Leibniz notation, and it has several advantages. So first, what I'm going to do in Leibniz notation is that I'm going to specify an intermediate variable y here. Remember, our goal with the chain rule was the derivative of a composition. You had an inside function and an outside function. So what we're going to do is we're going to give that inside function, the g of x, a variable name. We're going to call it y. And then we can translate this entire thing that the derivative of the composition is the derivative of this function f with respect to the variable, derivative df dx. And then since the chain rule is the product of two things, in Leibniz notation we get a product of two things as well. The first of them is the derivative of the function not with respect to x, but with respect to y, with respect to this inside function. And then you multiply it by the g prime now turns into dy dx. One advantage of writing it this way is that in practice, when you have a whole bunch of different variables going out, so then when I write these primes up here, it's not always completely clear which variable am I taking the derivative with respect to. And when you do the Leibniz notation, the df dy, it tells you you're taking the derivative with respect to y. And then when you do dy dx, it tells you you're taking the derivative of y with respect to x. It's very explicit and clear about which variable you're taking the derivative with respect to. The other advantage that I like this is that I think it gives the intuition behind the chain rule a little bit more clearly. So let me think about the dy dx. What we have here is that if I change x a little bit, a small amount dx, then we get this little change in dy. That's what dy dx means. It tells me how much is the y changing when I change x a little bit. And then when I look at df dy, this is similarly how much is my f, is the top changing when I change the y a little bit. And then if I think about what's happening with a composition, with an inside function and an outside function, you change the variable a little bit and that changes the y. Then now that the y's changed a little bit, you're going to be changing the outside function. You're going to be changing the f. And so I think that it makes it a little bit more transparent why the chain rule is these product of these two things when it's written in Leibniz notation. Now, I have to caution you. Be careful. Resist the temptation to say, well, look, there's a dy down here, there's a dy down there. Why don't I just cancel those two? This doesn't work. This df dy is thought of as a single symbol. It is one concept. It is one function. It is one number at any particular point. So I don't want you to think of this as four different symbols that have been divided and where you can do normal canceling. I think you want to think of this as two different symbols, one df dy and the other dy dx, and you can multiply them together, but there's no form of canceling. Nonetheless, as a sort of a mnemonic or heuristic to how to think about the chain rule, it is the case that df dx is what would have happened if you were allowed to cancel, even though you are not. Let's see an example. Here I have kinetic energy, and kinetic energy depends on, well, the mass and also the velocity. Now I'm going to assume that the mass isn't changing, but the velocity, it for sure can change. If I'm driving my car and asking what's the kinetic energy of the car, well, it depends on how fast I'm driving, and my velocity function is a function of t. So something I might be interested in is how much is my kinetic energy changing with respect to time? In other words, I might be interested in taking the derivative of energy, kinetic energy here, with respect to time. Now, what the chain rule is going to say is that there's not a t explicitly in the kinetic energy formula. Depends on m, which we're treating as a constant, depends on the velocity, but there's no t immediately. It's only then that the velocity is itself a function of t, that the t sort of sneaks its way into the kinetic energy formula. So what I'm going to do is apply chain rule to this composition. The energy depends on the velocity, and the velocity depends on the time. I have a composition. And so I'm going to say by chain rule that this is the change in energy with respect to the velocity, and then I have to multiply by the change in the velocity with respect to time. And I have this particular product that gives me the chain rule. Now, I'm going to figure out what the change in energy with respect to velocity is going to be. Here I have my formula, and I'm just going to come along and take its derivative. So the 1/2 is a constant. The m I'm treating as a constant, and then I have a velocity squared. taking the derivative with respect to velocity of velocity squared. So this is going to be 2 times v. So that's the change in the energy with respect to the velocity, but then I have to multiply by the change in the velocity with respect to time. And so I'll multiply on the outside by dv dt, and if I'd given that to you, we could have done that computation as well. And of course, the 2's will cancel here. So this shows us how we can take the derivative of one variable with respect to another variable, even if there's sort of intermediate variables, because our function really is a composition.